the difference if you think, for example, the pink one is breast cancer in the incidence, but if you see in the mortality level, it's not the same level of mortality. So it means that this is a cancer that could be somehow cured, or there are, for example, the pink one is breast cancer in the incidence, but if you see in the mortality level, cancer. But it's not, for example, the same cancer, level of mortality. Actually, if you happen to have this disease, it means that it's a very poor prognosis, so it's a very high mortality in this sense. So for example, the pink one is breast cancer in the incidence, but if you see in the yes, this is the cancer classification. So when we talk about cancer, we can refer to it either because of the location of the body, like I said before, for example, breast cancer, lung cancer, and so on. But we can also refer to it as the type of tissue that it originates from. It could be a carcinoma, a sarcoma, a myeloma, leukemia, and so on. We can move next. So what is cancer? The definition of cancer is actually a genetic disease because we have normal cells in different tissues, but something happens at some point and these cells start to mutate. So they get mistakes in their genomic, in their genome basically. And so they start to behaving in a way that is not normal anymore. Usually they start with abnormal growth. And then this can also start to be local or normal growth, but then you can also start to go around and have an invasive disease. And the problem with cancer is that because there is this invasion, the normal tissue cannot do their job anymore. So the lethality, let's say, or the problem with cancer is because now you have abnormal growth that is interfering with the normal function of the organs. We can move forward. So this is the steps in tumorigenesis. So the cancer is actually a process. Not everything happens in the very beginning. You usually have an initial source of mutations that can create some different phenotype. For example, one is the abnormal growth, the other is the inability to die if there is some extra problem in the genome. So basically the cell is keep going and dividing even if it accumulates more and more abnormalities. And that creates this cascade of events and also this diversification of the subclones of the tumors. So you can have a very heterogeneous population of cells, and the cells can have different mutations in different places, basically. So you will have not just one let's say disease, but is actually a very diverse type of disease within the same cancer type. Next. So one concept that is also spread in the field is that you can have, because of this evolution of the cancer, you can have different type of mutation. You can have trunk, let's say, mutation and branch mutations. The trunk mutations are the ones that are happening at the very beginning. Usually they are the drivers and they involve genes that are very crucial, for example, for cell cycle, proliferation, and so on. And usually this mutation happens earlier on in the tumorigenesis process. And so most of the cancer cells have this mutation. But then the more they go along, they somehow accumulate other passenger mutation or branch mutation. And those are the mutations that make the cancer cells so diverse with each other, because they keep accumulating basically random mutation as they go along. Next. So what causes cancer? So it's a genetic disease. So it could be sometimes that you're born with certain mutation and they just get more, let's say, severe, or they get triggers from the environmental. Usually you have 2 copies per genome of certain, crucial, for example, oncogenes, and let's say that you are born with one copy that is already mutated. If you have an injury from outside, it could be smoking, it could be sun exposure, it could be some other radiation, something, then you have much higher chances to get also the other copy of the gene mutated, and then suddenly you have both copies that are not doing their job anymore, and then you can have accumulate. So that can increase your risk. But even if you have both copy as normal, you can still have environmental factors that can trigger cancer. And viruses is also one of these. There are some viruses that, because of different reasons, some is because they integrate in the genome, and so they also promote this kind of abnormal expression of certain genes. But some others, they just create a lot of inflammation, a lot of problems around that triggers cell division, and the more a cell divides, especially if there was not meant to divide that fast, then the more chances you have that every time that they divide, they actually make a mistake, and so they create mutations. Next. So there are some treatments available for cancers, and the crucial thing usually is to discover the cancer early, and even better if you can prevent certain risk factors. But if there is, the highest chances is to discover basically this disease early, because still now surgery is one of the best treatment options. Then we have other ways, chemotherapy, radiation, immunotherapy. That what we will talk a lot different in the next slides. And we also have different treatment approaches depending on the stage. So when it's really the end, it's usually just palliative care. That means improving the quality of life, but there is no really hope to cure. And then we have clinical trials. This is when instead, let's say, like there is maybe the patient is still terminal, let's say, or advanced, but there is still hope to maybe try some new experimental drugs. Then we have personalized approach. So far, these are also still under mostly clinical trials, or we have off-the-label drug use, which means that you can try a drug that was meant for something else and see if it can be used for cancer treatment. And this is also usually happens within more experimental settings. Next. So now we continue with focusing more on immunotherapies. So immunotherapy is one of the therapeutic approach that you can use against cancer that really is using immunological elements to fight the cancer. So you can use elements of the immune system like antibodies, immunocells, or small molecules like cytokines, for example. And because we have so many options, we can talk about immunotherapies as plural, and there are also a lot of combinations that you can do with the different approaches. So here I listed some. For example, you can have monoclonal antibodies, but within the monoclonal antibodies, you can have some that target cancer antigens and then induce basically cell death, triggering other cells that go and eat, let's say, and kill and eat the cancer cells. Or you can have monoclonal antibodies that are directed against immune cells. So, for example, checkpoint inhibitors, they are binding to T cells and they inhibit their inhibition. So they basically help them to restore their functionality. Then we have other immunotherapy like non-specific immunotherapy when you give cytokines, and this boosts in a general way the whole immune response. Or you can have transfer of cells that could be either normal cells, non-genetically modified, or you can have transfer of cells that are engineered, adding maybe a CAR or a TCR before you actually give it back to the patient. And then there are also usually are therapeutic, so it means that you get this vaccine when the cancer is already there. But there are some vaccines that are considered also preventing for cancer, specifically the HPV vaccines, because preventing the infection helps you, and this is a cancer that is related to the viral infection. So preventing the viral infection, you can also prevent cancer. Next. So this is a list of all the possible, or not maybe all, but most of the antibodies and small molecules that are used now for therapy against cancer. Some of them are approved. Some of them are still in more like a exploratory, let's say, phase. Next. This is the same list. I don't want to go too much in detail because it's a lot, but I put it there so you can have it, as a reference. So these are like cell therapies that are in use now. Some are also approved, like CAR-T, for example. We know several commercial therapies. Some are still getting, approved, or like they are on the way in the clinical experimentation, like NK cells or CAR cells. And then there is a whole new field about the iPSC derived immunocells. This is mostly because it's a way to provide allogenic therapies for like a very large number of patients. Next. So how advanced are these therapies, and like when at the moment today? So if something happens, what kind of option the patients have? So for the hematological malignancies, there are quite several options now, and they are most advanced. So there are already commercially available products. That means that they have been through a lot of experimentation. They have been tested in a lot of patients around the world. And then they are recognized as a therapy that can be given as, within the standard approach. So it's like a drug that, let's say, a doctor can prescribe as a treatment for this patient. The hematological malignancies are the one where you not only have the best or like the most widespread use, but also the best success. So this is where this type of therapies work the best so far. For solid tumors, we have some good therapies. The best one is the small molecules, in the sense of like monoclonal antibodies, where you can use checkpoint inhibitors, either anti-PD-1 or anti-CTLA-4 or anti-PD-L1. So this works in a different, let's say, different levels. So some cancers respond very well to these therapies, so you get very high success, like melanoma, for example. Some other are a little bit less responsive, and so for those cancer, you don't really have much benefit from these therapies. So most of the problems, let's say, that we have is really against solid cancer, and this is where really we need to find better immunotherapies. Next. So why do we have all these problems, or like why they are still not so widespread? Why don't we have that more? So there are particular challenges with these therapies, and they have to do not only with how the therapy really works in terms of efficacy. That is really one of the major factors, but there's also other things related to it. For example, even if you have like good results with the therapy, there could still be very high toxicity associated to that. That means that the hospital that has to treat this patient need to have a very, very good infrastructure for the patients. So they need to have like intensive care units. The medical team need to be trained to understand this toxicity and to manage. So that can be a challenge for some hospitals. Another challenge is the manufacturing and the logistics. So most of these therapies are still based on autologous cells. So it means that you need to take out the cells from the patient, do something with it, maybe genetic modification, and then put it back. So it could be that there is a lot of problems in moving these cells around. Maybe the center that harvests the cells is not the same that does the GMP manufacturing. Then you have to ship it back. So it can be a lot of like complication around this, and that can not only increase the cost, but can also increase the risk that something goes wrong on the way. And these patients typically don't have much time to wait. So it's really crucial that things work very well and efficiently. The other aspect, it's more like, let's say, at the government, let's say, level, or more political things, is like the health technological assessment. So whenever a government, or a public or any healthcare system basically has to decide how do we reimburse this treatment. Is it the patient that has to pay? Is it an insurance? Is it within the public system? So they need to have good data to decide what to do, and they also need to negotiate the price basically if there is a company providing that. And this could be a challenge in some countries, because the cost of these therapies are still very high. So it could be that it's a problem to offer these therapies to all the patients. Next. So this is just a summary by category, basically what I have for immunotherapy, how they work, and some key examples. But we can go to the next one. Okay, this I don't see anything, but so this was supposed to be the cancer immunity cycles. So now you have to use some imagination if you don't see like I don't see it. But when we talk about the previous lecture in the course, we talk about antigen presentation and stimulation of T cells. So the cancer, in theory, should follow the same path. So if you have a cancer cell with a mutation, there should be mechanism in the immune system to discover these cancer cells and kill it. So if there is a mutation that is presented on the MHC class 1, then we should have a CD8 cell killing it. If the HLA, for example, is downregulated to escape the CD8, then it should be an NK cells coming in. But many things can happen in this cycle, and many things can go wrong. So it could be that either there is no efficient presentation of the mutation, either there is inhibition of the cells, or many things can go wrong, and that can impact basically the ability of the immune system to fight this cancer. Next. Yes, so this is an overview of the pioneering immunotherapies from Steven Roosevelt, and I'm bringing up Steven Roosevelt because that's where I trained as a postdoc, but he's really one of the most prolific, let's say, scientists and medical doctors that really was one of the first, more than 40 years ago, to believe in immunotherapy to actually treat cancer. And a lot of his, initial inventions and approach are now resulted in therapies that are approved for use in patients. So this was not just a clinical experimentation. Now these approaches can be given as a treatment. So one of the earliest one was high-dose IL-2. So IL-2 is a growth factor for T cells. So giving IL-2 in general boosts whatever T cell immunity you already have in the patient. So if the patient has some problem in that, this is basically an external kick to the immune cells, hoping that there is some tumor specificity in those cells that they can actually fight the tumor. Another therapy that is approved in US now is the tumor infiltrating lymphocyte therapy, and we will discuss this approach more in details. But it's basically taking out T cells that were already capable of reaching inside the tumor, grow them outside the body, and give it back to the patient. And then the last one is a CD19 CAR. That was the first one approved for adults as well, and is now used. It's now a commercial product in many countries. Next. Yes, so this is now we are starting to look more into the tumor microenvironment and what is the what does it look like inside the tumor. So we think about the tumor as one uniform agglomerate of cells, but in reality, it's more like one example that was used in the Rosenberg's group was like really a fruit salad. So you have a lot of different components, and it's not only tumor components, you have also immunological components that are there infiltrating, trying to do something with these cells. And in particular, the approach on the surgery branch was to focus on the T cell, so CD4 and CD8 T cells that are already infiltrated in the cancer, but for some reason they are not able to kill all these cancer cells. Next. So the approach that was used and was developed was to try to understand why these cells that are there together with the cancer, why are they not killing it? And back then, originally, they didn't know about exhaustion and immunosuppression and so on. But intuitively, they said, okay, let's take them out. So they did a surgical resection of the tumor, chop up the tumor in little pieces, and then put these pieces of tumor in like a bath of high-dose IL-2. And then the wells the cultures from these species that were able to grow out T cells, they were basically pulled together and then given back to the patients. But this patient was also preconditioned. So they also did some other combination of therapies to this patient to really limit the tumor burden and also try to prepare the environment for these cells to come back and don't have any more competition from the original cells, let's say the normal cells that are just circulating in the body. So they wanted to condition the patient so that the new cells coming in, these TILs, expanded TILs, had the best chances basically to find cancer. Next. So now I told you that it was a surgical resection, and that's what was originally used. Now you can have TILs of different origins as well, because moving forward, when people started to try maybe different tumor types or different, try to make it more easier, let's say, to reach the patient, they try different places. So you can basically take out a primary tumor. This could be sometimes really complicated to take out surgically, and it could be that the primary, if it's, let's say, the old one, maybe is already necrotic, so maybe you don't have very nice T cells inside. Another option is to harvest from a metastatic lymph node. This is usually easier because you can access, maybe peripheral lymph nodes like under the armpit or something like that, if they are metastatic, and they can usually give way more T cells in good shape. Or if you have, it's also possible to try to extract these T cells from a tumor biopsy. This is when really either the location is really difficult to reach or there is just maybe other problems, so you have to do a very minimal invasive. But depending on what you choose, basically, you can have different reactivity as well. This is how you prepare the TILs. So the initial protocol was to fragment the TILs and put it in, one little piece for every well. But then there were other type of preparation. For example, the GentleMax, the mechanical and enzymatic digestion, enables to have one culture instead of having all these little pieces that are, each one is a different culture. You can take the whole mass of the tumor, digest it, and then with that you can, for example, decide to sort out a specific population, maybe cells that express PD-1 or 4-1BB or something else. Next. So once you have extracted these cells, you need to expand them because you need to reach a very, very high number of cells to then put it back in the patient. And there are different ways to expand these cells. One obvious choice is IL-2 because that promotes growth. But over the years, there are other protocols coming that use other cytokines to preserve maybe a more, let's say, younger phenotype or certain type of effector functions that otherwise would be maybe lost. Next. So one important thing to remember is that whenever you have to do with a TIL product, it's something that you cannot really control too much. So it would be very different from patients to patients. And it's also not really one single therapy, it's more a combination of therapy. So you have the T cells, you have IL-2 that you're giving, you have preconditioning on the patient, and there are several now explorative products or TIL variation, let's say, that try to focus on different characteristics of the TILs, but still it's very few, I think, centers can actually provide the competence or the knowledge to prepare these TIL products. Next. Okay, so I don't remember if there is anything after this. Is it already the article? Yes. Okay, then I leave it to you if you want to have questions or how we move forward.
Pode não? Tá. Gente, vocês querem fazer perguntas? Estão me ouvindo? Pessoal que está online? Podem abrir o áudio. Tem perguntas lá no... Ok, uma das coisas que a gente pode ver é que não são terapias fáceis, né? A gente viu vários desses conceitos na aula, mostrando, né, as diferentes vias que precisam ser moduladas quando a gente tem, né, a resposta das células T. E essa imunorregulação é muito redundante, né, e tem muitos aspectos que podem levar a que a gente tenha, né, diferentes resultados, né, de uma pessoa para outra. O fato também da gente colocar essas células in vitro, o que vocês acham? Isso pode ser uma limitação? and I'm trying to discuss with them about the microenvironment. So those therapies in which we select those, we extract those cells from the tumors, they will then stimulate them with these antigen and cytokine preparations. They could have limitations on this aspect. Would you like to comment a little bit about that, about how these can...
Yes, yes. So there is, one is the source. So we don't know how the tumor is, and that's why TILS therapy, for example, has been tried on several tumor types, but not everything is successful, and that has to do with the capacity of the T cells to enter in the tumors. And maybe you heard like some people say hot tumors and cold tumors. I mean, some tumors are just more easy for T cells to infiltrate, and that's usually the one that respond better to immunotherapy in general, because the T cells are already there. So there is already something that is, the T cells can see. It could be that maybe there is still, an inhibition, but that can be reversed in an easier way. And other tumors that just maybe don't even attract T cells because they are just not immunogenic. So it could be that the antigen presentation is not efficient, or the mutations, let's say the possibility to recognize these tumors is very limited. So in a sense, the immune system doesn't really see much on these tumors to go and infiltrate. So when we take out the T cells now for preparing the TILs, we have to recreate an environment that is, very favorable for them. So typically for TILs, we use something as antigen-presenting cells that are actually allogenic. So these are like feeder cells, usually PBMCs from other unrelated, individuals, and they offer like co-stimulation because we don't know what antigen these cells recognize. So we can't really go in and give a specific antigens to recognize. So we just say, well, we just give something very broad. Usually it's 3 different donors with hopefully different HLA types. So we give some sort of like unspecific co-stimulation to the T cells just to get them to activate and proliferate. And then we give also targeted stimuli for anti-CD3, for example, that still is another unspecific boost for growth, and a very, very high dose IL-2, because these cells basically, to be able to offer a therapeutic option, they have to be expanded to several billions of cells, and then they are given back. So the theory is that by removing them from the original tumor microenvironment, you remove also the whatever inhibition maybe was there, and you give them a break in a sense from this very hostile environment from them, and then you provide some positive stimuli, so cytokines and then unspecific stimulation. Some studies also have been trying to select against specific antigens, but that's usually very difficult, and in that sense it's the other preferred option is to just transfer the specificity by transferring a CAR that already recognizes the antigen that we want, or a TCR that already recognizes something that we want. So more than try to fish out things from an existing culture, one typical approach is to just transfer the specificity like that.
Very good. And what about the age of the patient? As we understand that age is a primary driver of immunosenescence, and there may be a total, a more broad, difficult condition for the T cells to be able to expand and to be activated.
Yes, it's definitely a factor. So, and it's in essence just because of age, but it can also be some sort of like induced senescence state due to the pre-treatment. Some chemotherapies, for example, have an effect on the lymphocytes that looks like really aging them, or just making them not able to proliferate as good as they would otherwise. So sometimes it is both the age of the patient, but also what happened to this patient in terms of pre-treatment that can really inhibit these cells, especially the proliferation capacity.
Very good. Tem mais perguntas, gente? Tem uma pergunta aqui, só um instante. Então, there's another question from the audience. Eugenia asks if using liposomes with tumor antigens as a vaccination or direct presentation to isolated lymphocytes would be a possible methodology.
Yes, I think that they tried several ways. It's the challenges with these therapies is to have enough antigen presentation and to present the right antigens, which is always a gamble because we don't know what will generate a response in the patient. But you can have lysosomes either ex vivo, so you can basically transfect your antigen presenting cells and then give it back. Or I think there is also some testing in maybe trying to deliver these antigens in different ways to important location, for example, lymph nodes, where you know that the T cells normally needs the antigens. So if you try to inject the antigens there, maybe you boost this response. But it's very tricky to generate, strong responses in cancer patients, especially at the advanced stages.
Okay, thank you. Do you have your camera so that we could finish the session? Yes, thank you.
Yes, I was a bit afraid of the connection.
Yes, I'm so happy that we could surpass all the problems and
Yeah.
And thank you very much. We will move with the class. I don't know how we are about the time. Can you still discuss the article with the students?
I have time to stay if you want.
Very good, very good. So I'm just going to say goodbye to the rest of the audience and we can proceed. Então, gente, muito obrigada por estarem aqui assistindo a nossa sessão. Espero que tenham tido um bom a oportunidade com a doutora Ana e a gente vai continuar com os alunos da disciplina, tá bom? E aí, para o compartilhamento com o YouTube, qualquer coisa. Ok, eu vou tentar project now the